Ella, can you hear me now?
Yeah.
Um, Thank you for sending me that homework a little bit early. When I glanced at it, I realized I had done that hyperbolic sign thing, but you had it figured out, so that's fine. Thank you. Didn't realize I had done that. I think I looked at it and thought it was a sign. Okay, another good Friday. Let's see who we got. Allison, Brittany, Isabella, Jessica. All right, we're waiting for a few more people. Guys, have any questions about anything before I start sharing the screen and so forth? Anybody have any questions? The test, we've already done everything that's going to be on the test. So anything I do new after a Cauchy-Euler equation will not be on this next test. So the homework you have to get in, I believe, is still on Cauchy-Euler equations. I haven't quite finished Cauchy-Euler equations. I'll do that today. But you've got plenty to work on there, but it will be the last thing that'll be on the test. So, and I think I've got everybody's homework back that sent me their homework. So we're good there. And I don't think there's going to be a whole lot to do this weekend except just work more on Cauchy-Euler. And then I'm going to introduce one thing today that I'm not going to give a whole lot of work on this weekend. Okay. Anybody questions about the test or anything in particular? All right, let me share the screen while we're waiting for people to come in here. Let's see here. There we go. Okay. All right, I'll see. I've got 1, 2, 3, 4, 5. I've only got a half here. Oh, there's one, Christina. I'm over half. Got Christina in. All right, let's, while we're waiting for a few more people to come in, let's just review what we did with Cauchy-Euler equations. And then take a look at the one thing I didn't get to do. If you remember, when we were doing other types of equations with constant coefficients, we had 3 cases that we looked at. We looked at the case where we had distinct roots of YC, and we had repeated roots, and then we had complex roots. What we did on Wednesday for Cauchy-Euler equations, and let's just recall too what a Cauchy-Euler equation is. It's an equation with instead of constant coefficients, it has these powers of x in them, and the powers on x match up with the order of the derivative. Okay, so that's Cauchy-Euler. We can solve it in all the ways we've been talking about, and we can also solve a non-homogeneous one by using variation of parameters. So we're going to use that again with these kinds of equations, as well as with the ones with constant coefficients. So that's what a Cauchy-Euler equation is. If you recall, then what I looked at was a second order one to sort of get started. I tried to take this thing in cases, and we found out how to find the characteristic equation by plugging things in. And this is all my junked up stuff we did on written on stuff we did Wednesday. We get 2 distinct real roots. We prove that if you have 2 distinct real roots, they look like y equal x to the m1 and y equal x to the m2, where m1 and m2 are the roots. If you have 3 distinct roots, same thing, it'll be another y equal x to the m3. So I don't think I've really done one of third order yet here, but it works exactly the same way. One thing we did discover about second order was that the characteristic equation always took a certain form, and that certain form was that the coefficient right here on the y prime was b minus a. Okay, we showed that, so that you didn't have to go through this process every time with a second order of finding out what the characteristic equation was by plugging in your x to the m and so on. So that was pretty easy. Several of you gave me the we did show these were linearly independent, and we can We're okay with that. So we've got a fundamental set basically here for something of order 2. All right, the second thing we did was repeated roots. And we showed that the way we talked about this is, well, if we got one root, what would it take to get the other root? And we used that method from 4.2 to create another linearly independent root. And what we learned about that was that that second root, if the first root was x to the m1, the second root's x to the m2 times log x, okay? The same idea is going to happen for 3 roots, okay? We'll go back and talk about that in an example in a little bit. So on this one, we ended up having repeated roots, a repeated root of -1/2. So the YC was C1x to the -1/2 and then C2x to the -1/2. If the multiplicity is bigger than 2, every time you step up to one of those other roots, you'll have the same xm1 in everything. That's the root that's being repeated. And you'll step up powers of this log x, much like we did with x powers on x when we had e to the x kinds of roots in equations with constant coefficients. Okay, so what we didn't do was complex roots. Okay, question anybody about just getting up to this point? Everybody okay with that? Doing okay? All right, so let's look at complex roots. Complex roots are going to behave in a lot the same way as what we had with constant coefficient DEs. If you think about what the root is, if you have, remember, complex root come in conjugate pairs. So you have a plus ib, where I is the imaginary, with the I, there's beta is the, well, it's alpha plus I beta. Beta is the imaginary part and alpha is the real part. Now, if we were to say, well, why can't we just write this root like we wrote the other ones, x to that root and x to that root? And the fact of the matter is that you can, but it's not the way we leave it. And what we do to rewrite it in a particular form that's more standard, I guess I would say, is use Euler's formula again. Okay, if you remember, that's an important one. Euler's formula just looks like that: e to the I theta is the same as cosine plus I sine theta. So what I'm going to try to do is use Euler's formula to break this thing down and put it in a little different form than what you're used to seeing. Right? Before, when we put it in a different form, it looked like e to the alpha x times c1 cosine beta plus sine beta. So we use the real and the imaginary parts to write something in terms of alpha and beta. Okay, so here's what I'm going to do. I'm going to say x to the alpha plus I beta is x to the alpha times x to the I beta. Just break it apart. So I have that x to the alpha up there, and of course that's just going to be x to the real part of the root. And then I'm going to do one other thing before I change this using Euler's formula. And it just turns out to be a nice thing to do. If you look at e to the I beta log x, and you rewrote it like this, what is e to the log x, guys? What do e and log x do to each other? Somebody on mic and tell me what's going to happen with e to the log x. Anybody?
They cancel out.
Yeah, they undo each other. Exactly, they undo each other. So I could write x to the I beta as e log x I beta. So that's what I'm going to do. I'm going to write x to the alpha e log x I beta. So that's the same as x to the I beta. Now, if I look at that a little more carefully, again, that thing right there is the same thing as x. So it's the same thing as x to the I beta. So multiplying powers here, I get I beta times log x, and I get something that looks like that. Now I'm going to look at it and put it in Euler's formula. Euler's formula says e to the I beta log x, which is what we just showed here. That could be written like that. Your imaginary part is that beta log x. So Euler's formula says that's going to be cosine beta log x. So that's your angle, cosine beta log x plus I sine beta log x. If we do it with x to the minus I beta, we just have a minus in here. It'll be cosine minus beta log x plus I sine minus beta log x. This is looking a lot like what we did before. But the two things I want to look at are this piece, and I want to look at this piece right here simplified. We know the cosine of minus an angle is the same as the cosine of the angle. And we know that the sine of minus an angle, the negative sign comes out. All right, so that negative sign on the angle is going to come out there. So I want to look at the one above it and this one right here below it. Similar thing we're going to do to find out what our fundamental set is. If you look at, and we know that we could show that we've got a fundamental set here, but I've written it in a different form, so I want to look and see what happens. If we look at this equation and this equation, and I add the two together, notice that the I sine beta log x and the minus I sine beta log x will drop out. That's like letting C1 and C2 be something so that one thing drops out and you can see basically what's left from the other, which ends up being part of the fundamental set. So if I do that, these two right here drop out, all right? And I'll add these two together and I'll get 2 cosine beta log x. All right, I don't really need the constant. The constant can be sort of considered as, say, C1 or C2, whatever you put on it. So the basic part of this is that one of the members of the fundamental set, or part of it, is cosine beta log x. Okay, that's the imaginary part of that thing. On the other hand, if you look at these same things right here, and you subtract this one, so you subtract that whole thing there, what happens in that one is that the cosines drop out, and this minus subtraction changes that sign right there, and then you get some signs. So in other words, you get 2i, all right, 2 of these I sine beta log x's. Again, doesn't matter about the coefficient on there. It can be worked into the answer later. But what happens here is that the fundamental part of that looks like that. Okay, so what happens here then, guys, is that when we look at the YC, all right, it's going to end up being x to the alpha. I'm pulling that out, all right, because remember it was x to the alpha plus beta. Okay, it looked like this, x to the alpha plus I beta, which of course is just x to the alpha times x to the I beta. And the x to the alpha gets pulled out, all right? And the what's left then is C1 cosine beta log x plus C2 sine beta log x. And what we've got is that these two things right here are linearly independent, okay? And actually I should show, I put another bonus on here, but these two are linearly independent, but the actual fundamental set each one of them has an x to the alpha in it. Well, that looks like an infinity there. Let's get rid of that one. That's x to the alpha. So you've got a fundamental set here. X to the alpha cosine beta log x, sine x to the alpha sine beta log x. So another bonus points if you're interested in it, take those two things there with the x to the alpha and show that they are linearly independent. Again, just using the Wronskian. And alpha is just a real part, for instance, so if you want to differentiate it, it's going to be alpha x to the alpha minus 1. Okay, so it's just a real part, and you would use the power rule on it. Okay, so what we've got here then is that our YC, when we have complex roots in a Cauchy-Euler equation, looks like this. x to the real part of the complex root, and then C1 cosine beta log x, where beta is the imaginary part, okay, the part with the I, plus C2 sine beta log x. All right, so that's the third case. All right, let's do a problem. We'll call what we did on Wednesday. Suppose I had 4x squared y double prime plus 17y equals 0. If you remember what I did to get the characteristic equation, I said that one of the roots look like x to the m. So just sort of a reminder here, y is x to the m. That made y prime m x to the m minus 1. All right, and it made y double prime m times m minus 1. I'm running out of room over here. M minus 1 times x to the m minus 2. All right, just remembering that. So that's what I plugged in here. I had 4x squared. Y double prime was m minus 1 x to the m. Okay. And y was just x to the m. If I multiply this stuff out and pull out the x to the m, I wind up with 4m squared minus 4m plus 17. Now, again, let's talk about the shortcut, because you're totally allowed to take the shortcut here. If you remember this, there's no y prime showing here. So that's 0 y prime, okay? So basically what we know from this equation was that b was 0, the coefficient on y prime was 0. A, the constant coefficient on y double prime was 4. We knew that in the characteristic equation, what happened is that the second term right here ended up being b minus a. So it's 0 minus 4, and we got a minus 4m. Don't have to plug this in all the time. Okay. Is everybody okay with that? So if you have a second order Cauchy-Euler, you can use that rule. Okay, so let's find the roots. If I look at the roots, I got minus a minus 4 plus or minus the square root of minus 4 squared, minus 4ac. Playing that out, guys, pulling out the common factor and seeing what's left under here is the square root of minus 16. Square root of minus 16, of course, is 4i. Times the 4 that I could pull out of this. If you looked at that number, you'd see you could pull out a 4. You'll wind up with 4 plus or minus 16i over 8. Doing the division there, I get 1/2 plus or minus 2i, which says that alpha is 1/2 and beta is 2. Okay. Now, I'm going to add some conditions to this one too, so we'll go through some of what happens when we have conditions, but let's look at what YC is. YC, we said when we had complex roots, was going to be x to the real part, so there's x to the 1/2, plus C1 cosine 2 log x. The 2 is the beta. Okay, so there's 2's beta. This thing right here is alpha. So there's my complementary solution there. And since this was a homogeneous equation, that's all I have to worry about in this one. Okay, so let's see what we can do by using the conditions to find C1. We'll finish it up that way. All right, everybody okay on the form here? It's x to the 1/2, and then for every one of these roots, C1 cosine 2 log x, C2 sine 2 log x. All right. All right, let's look at the conditions. I've got these conditions. I knew that my YC, we go about finding the C1 and C2 the same way. We just found out that YC was x to the 1/2 C1 cosine 2 log x plus C2 sine 2 log x. If we take the derivative, we're going to have to use some product rule stuff here, guys. So first, derivative of this thing, be careful with this. The derivative of cosine is minus sine, but then you got to take the derivative of that inside, which will be 2 over x, plus the derivative of that, of course, will be cosine 2 log x, and then again times the derivative of the inside, which is 2 over x, plus the second thing times the derivative of the first, which is 1/2 x to the minus 1/2. So these get kind of messy because the the original solution is messy. YC is kind of messy. So I need that derivative. That's all I need. I need two, for a second order equation, I need two conditions, all right, to use. So one of my conditions was that y of 1 equal minus 1. So I take the y here, and I just plug in 1. And this actually turns out to be pretty nice, because if I plug in 1 for x, it's just going to be 1 to the 1/2. C1 cosine of log 1 is 0. So right there, when I plug in 1, I get log of 1, and log of 1 is 0. So cosine of 0, which is what this ends up being right here, is the 1 that I get right here. Okay? Plus the C2 sine 2 log x. Again, the log of 1, when you plug in your initial condition, is 0. Sine of 0 is 0, and that's where I get that 0 right there. So right away, by knowing y of 1 is minus 1, we get minus 1 is my C1. Because that thing drops out, I've got 1 times C1, and the condition said it had to equal minus 1. Okay, so the second thing I'm going to do is use my second condition. And my second condition says that I'm going to plug y1 into the derivative, and it should be 0. So when I plug it into the derivative, I get 1 to the 1/2. Now here's what I'm plugging it into right now, guys. There's the derivative right there. Okay, I'm plugging in 1 all the way across that thing. So it's going to be C1. The sign, that'll end up being the sine of 0 again, which is 0, and 2 over 1 just gives me a 2. That's going to wipe out. All right. If I plug in 1 right here, it ends up being 2 over 1. And then again, the log of 1 is 0, but the cosine of 0 is 1, and that's where I get this stuff right here. Okay, from that first piece. The second piece is this second line right here. So again, I'm plugging in 1. That's going to be C1. Since log of 1 is 0 and cosine of 0 is 1, I get 1 out of that one. I go to the next one. I plug in 1. The sine of 0 is 0. That's where I get that. And then I plug in 1 to this thing, and 1/2, 1 to the minus 1/2 is just 1. So I end up with, looking at this whole thing right here, I end up with 2C2. That drops out because of that 0. So I end up with 2C2 right there. And I end up with, this thing is 1/2. So that drops out right there. So I get 1/2 C1 is equal to 0. All right, that's pretty nice. It's easy to solve. We already know what C1 was. C1 was -1. So if I put C1 equal -1 into that thing, I get 2C2. 2C2 minus 1/2 equals 0. Move the 1/2 over, divide by 2, and I get C equal 1/4. Okay, so I can go back and write what this solution is. C1 is -1, C2 is 1/4. So it's actually going to look like this. That's going to be a -1 right there, and that's going to be 1/4. Okay, and that'll be my solution to my homogeneous equation. Okay, let's do one of higher order, so we can. I don't think we've done one of higher order with Cauchy-Euler yet, so let's do that. Unfortunately, I don't have a lot of shortcuts I can use with this. So what I am going to do is go ahead and plug this root in, which we would take derivatives of, and we know it looks like y equal x to the m. And if I look at the third derivative of that, well, let's sort of go backwards here. The first derivative would be m times x to the m minus 1, so that would go in there. The function is x to the m, so that would go there. The next derivative, the second derivative, would take this first derivative and bring the m minus 1 down. So that's going to be m times m minus 1, x to the m minus 2. And then the third derivative is going to take the second derivative and bring the m minus 2 down, then leave me with an m minus 3 right there. Okay, so all of this right here, plugging it in, all right, plugging it into this thing right here. Now, I remember Haley asking me a question on Wednesday, how did I go from this step to that step? Every time, and this is what makes Cauchy-Euler equations nice. And if I look at this and this, so what came from the derivative and what was actually out there because it was a Cauchy-Euler equation, when I add those powers, I get x to the m. That's going to happen every time here. X squared, x to the m minus 2 is going to be x to the m. X times x to the m minus 1. Again, that's a first power. Added, I'll just get x to the m. There's an x to the m in the last term because that's what y is. I can always pull out x to the m. Okay, always works like that. Now, when I pulled it out, I would have been left with, and I've sort of gotten ahead of myself here, but that's x to the m, x to the m. When I pull it out, I'm left with this. And I did a little work on that after I pulled out x to the m. I multiplied these two together, and that one. And then what was left in this one was 5 m squared minus 5m, right there, plus 7m plus the 8 right here. Now, you can see pretty clearly there what you've got is a cubic. Notice the term here, that's going to be m cubed. There's only going to be one cubic term. So when I crank all this stuff out and combine things, I'll get an m cubed. I would also get a minus m squared, that, and also a minus 2m squared, which would be minus 3m squared. And if I added it with the 5m squared, I'd get 2m squared. Same thing for the m terms. If I add the m terms, I get this, and I get plus 8. So what I've got to do in this problem right here is solve that cubic. Now, let's step back a minute on solving cubics. We had done some cubics where we had to use the rational root theorem, where the p's were the factors of 8. So plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. And the q's were the factors of that coefficient on the highest power right there. So plus or minus 1. So that's pretty easy. So the list of rational roots are all these over all those. And since they're all over 1, they're just these right here. So we could have 1 or minus 1 or 2 or minus 2 and so on. So we did that, and then we did some synthetic division once we found one. Don't ever forget, though, that you can look at this thing right here and ask yourself, will it factor? Because there are some cubics that will factor easily, and if you also remember, the technique for factoring some of these things pretty easily is factoring by grouping. Okay, so guys, suppose I grouped those two, and I grouped those two. You'll see that if you pull out an m squared from here, you'll get m plus 2. If you pull out a 4 from there, you'll get m plus 2. Then there's an m plus 2. There's a common factor that I can also pull out, and I'm left with that. Okay, so that's a nice thing. All right, so I didn't have to use the rational root theorem there. I didn't have to use synthetic division. It came out nicely because it factored by grouping. So if you look at the roots of that, one of those roots is m equal minus 2, right there. This thing, if you look at it, it's m squared equal minus 4. You can tell that's going to give you m equal plus or minus the root of minus 4, which of course those are two roots, 2i. Okay, somebody's either trying to get in or, there we go, there's Tierra. Let me get her in. Okay, all right. So, so we've got these roots, these complex roots that look like that, and one real root. Now, complex roots always come in pairs. That's why we get this this cosine beta, sine beta stuff. Okay. All right, Tierra, you're in. You're okay. I don't know if you can hear me or not, Tierra.
Yes, I'm
okay.
here.
Okay, good. Okay, good. All right. So, so let's look at what the solution looks like. You got one real root and this conjugate pair of complex roots. Your one real root's minus 2, so the part of the YC that associated with that is C1x to the minus 2. Okay, so That takes care of that root right there. Okay, right there. The 2i, remember that's a complex root and it's 0 plus 2i, so that's alpha, and 2 is your beta. So when I write the solution, remember it was x to the alpha, so in this one it's going to be x to the 0, and then we've already used up a c1, so c2 cosine, and then the imaginary part, 2 log x. So that's your alpha part, and that's your beta part of your root, of your imaginary root. Okay, so that's what the solution to that thing looks like. Okay, questions, anybody? I know on the homework what I told you last time was if you started the homework to look through it, and if you saw any complex roots, just don't do them right then. But now you can do all the kinds of roots that you've got. You've got distinct roots, you've got repeated roots, and you've got complex roots. Okay. Anybody question on that? All right. One other thing that we did yesterday was talk about what if we have Cauchy-Euler equations that are non-homogeneous. What we need to do is sort of follow the same rule we did when we were talking about constant coefficients. We solve for the YC first. Okay, we do what we were just doing, find the characteristic equation, write out what YC is. And you need your fundamental set. I solved this one right here. I got, so the roots were 1 and 3. Your fundamental set here then was x to the first and x cubed. What you want to do, and you need that because when we use variation of parameters here for non-homogeneous, we're going to need to use x1 and x3 in the Wronskian. That's going to give me this proposed solution, part of this proposed solution I've got here. Now, here's the thing that I told you yesterday. Do not forget. You have got to identify what this function is right here, but you do not identify it until you get this in standard form. So you've got to divide through by x squared. You've got to divide through by that, okay? Or you will get the wrong thing in your Wronskians. Okay, just real quickly, because we did this one yesterday. In the bottom, we put the two members of the fundamental set. We differentiate. We find the Wronskian at the bottom, which ended up being that. In the top, we put the 0 and the f of x after we had divided by x squared. So 0, 2x squared e to the x. And then the second column remains the same. That gives me u1 prime. Now we will remind ourselves of what u1 prime is in a minute. What gives me u2 prime? Same Wronskian in the bottom. Leave the first column the same, and in the second column put this. Okay, that's this variation of parameters is the homework you had due today. Let me say a word about that now that everybody's, I guess it's coming as here. I sent out an email last night, one of those problems, and unfortunately it was the first one up on the variation of parameters. There was a hyperbolic sign on the right-hand side. That hyperbolic sign can be written in terms of exponentials. Some of you may have done that in Calc 2, and maybe some of you didn't. But I think I looked at that real quickly and thought it was a sign. So it was a hyperbolic sign. You want to rewrite it in terms of the definition of hyperbolic sign, which is actually e to the 2x minus e to the 2x over 2. I gave it to you in the email, okay? So before you start that problem, rewrite hyperbolic sign. And I'll give you some more time on that. Just get it to me sometime later today, tonight, whatever, just so when I wake up tomorrow morning, I'll have something to do, which usually entails grading papers, okay? So if you haven't finished that, or if you haven't sent it to me yet, just send it to me by tomorrow morning, I'll say. Did anybody have a question about that? Did everybody get the email? I don't know if you've checked your email or not, because I sent that out late last night. I didn't see it until late. But check your email and you'll see what you need to do on that one. Okay, so finishing up this thing, what we knew is that we found using these Wronskians here, u1 prime and u2 prime, and remember we're using something called Cramer's rule. We found out that u1 prime was this and u2 prime was that. Our original hypothesis was that my particular solution looked like u1 y1 plus u2 y2, where y1 and y2 were members of the fundamental set that we had found. So in this case, I guess it's x to the first and x cubed. okay? So x and x cubed. These Wronskians give me u1 prime and u2 prime. But if I have u1, and u1 prime and u2 prime, I can just integrate them to find my u's, my u1 and my u2. So that's what I did. I integrated these things. One of them was a little tougher because it was using parts twice. The second one was easy. The general solution ended up then looking like the YC, which was right there. Okay, right there. And then the YP was the U1 that I found times Y1. And there was the U1, the U2 was e to the x times x cubed. Multiply it out and gather up terms, and then you've got the answer. Okay. You should have everything you need now to do those Cauchy-Euler equations. Be careful. I think there's probably one in there that's not homogeneous. Okay, there may be a couple that are not homogeneous, but they work the same way. All right, and now you have some. There's probably one in there that also has complex roots when you're doing the Cauchy-Euler things. Technically, these things are not due until Wednesday of next week. Now, that's pushing it, getting close to the test. If you can send it to me by Monday or Tuesday, that'll be great. I'll have it graded and sent out quicker, but it's due Wednesday by class time. Okay, that's Cauchy-Euler, and that's the last thing on the test. So so basically this test is just the biggest chunk of chapter 4, starting with 4.1 and going through. I have not done every section, so be careful that you know what sections, and I'll write what sections out and make sure I get that sent to you when you start to study for the test. We've had homework on every one of these sections, pretty extensive homework. I'm guessing this test is going to go pretty well. That's what my hope is. Okay. Anybody have any questions about that? Okay, I want to introduce one other new thing today, and I'm going to maybe give you one problem, and then I'll do more with this next week. This will not be on the test. The test gets cut off with what I'm doing, what I just did. All right, so let me look back at something else. Let's see if I can find it. This is the list of lectures we've had. Let's see here. It's hard to find things when there's so many of them. There we go, right there. Okay. Now, what I want to do here, go all the way back, is propose a problem. And this is why I want to introduce it and then show you a sort of an easy one to solve, and then we'll come back and we'll look at this in more detail. I'm sure you remember one of the very first things we did in chapter 1 was talk about what do we do with differential equations. And one of those problems had to do with one tank where water was going into the tank, all right, and coming out of the tank, and there was a mixture of salt. Maybe pure water would come in and I had so much salt in here, what happened to the water coming out? We could solve that with a linear DE. I think there's one on the first test, actually. Now, what we're going to do is sort of expand that idea. And I'm going to start with an application so you can see where some of these things come from, where I have two tanks. And let's see how I've got these two tanks set up. There's fluid with salt water, basically, and water, pure water, flowing in and out of these things in the direction of the arrows you've got. So if you look at this, if you start with this one over here on the left, we've got pure water being pumped in at 3 gallons per minute. All right, we're going to actually suppose that to begin with, tank A contains 50 gallons of water, in which 25 pounds of salt is dissolved. Okay, so there's water in here, 50 gallons, and there's salt in here. And we're going to assume as we go that everything's well mixed up. Okay, so the salt hasn't sunk to the bottom. Lots of these tanks like this that mix things have propellers at the at the bottom of the tank to continually keep it mixed up, okay? So I got 3 gallons of pure water per minute coming in. I then have 4 gallons per minute going this direction into tank B, all right? At the same time, the mixture in tank B, whatever it is getting recirculated back into A, all right? And then also going out of that tank at 3 gallons per minute and going back into A this way, 1 gallon per minute. Now well, it's more complicated than one tank for sure. It's not as complicated as it could get. There's some problems in the book that have 3 or 4 tanks, but let's just concentrate on this to begin with. The idea here is to find out how much salt there is in the tank at any time t. Okay, so let me just write, let's look at that. So this is what I just said. Once the process is started, the solution in each tank is well stirred and pumped out. It says construct a mathematical model that describes the amount of salt in each tank at any time t. All right, I'm going to let x1 be the amount of salt in tank A. All right, so x1 is the amount of salt in tank A at any time. Now, one thing we know about that from what we were told initially is that x1 at time 0 was equal to what? How much salt was in the thing when we began, guys? This is the beginning of the problem. So what is that? What's x1 of 0 equal to? If you read that sentence right there, what's x1 of 0 equal to? Anybody? It's gonna be, I'm seeing mic off if you're gonna answer.
25 pounds.
25, yeah, it's 25. So right away, I see that I've got an initial condition there. So we'll do, let me put a better 0 there. So I don't know much about the second tank, but I'm going to call it X2. I'm going to let X2 be the amount of salt in tank B at time t. It doesn't come out very well. It's cut off on the sides. And I'll ultimately be looking for X1 and X2. Now, if you look back, well, actually I didn't want to look back, so I drew the picture all over again here. Whoops, on the next page. If you look back at this thing, things are continually circulating, and there's stuff going in and stuff going out, and we're given these rates, the rate at which things are coming in. Okay, so what we're ultimately going to look at is the rate of change of the amount of salt, and if we can find the rate of change, we know we can go backwards and find out what the actual function is. I want you to notice something else about this one, because this makes this an easier problem. How much water, if you look at the total system, how much liquid is coming into A at any time? And look at the things that are pointed towards A. Look at the whole system and tell me how much is coming into A at any time, guys.
Or
yeah, I'm hearing it. 4. You got that 3 right there and that 1 right there. It's coming in at 4. All right. If you look at how much is going out of A, it's going out 4 going out. So you're really things are remaining sort of stable here. It's getting mixed up a little different. It's getting different amounts of salt in it, but it's still got this 50 whatever gallons of mixture in it. Okay. Now look at B. If you do the same thing there, what's coming into B is 4. What's going out of B is this 1 right here, and the 3 that are going out the tail end. So it's getting 4, and it's actually shedding 4. So again, those are not changing. The amount of mixture in there is not changing. Okay, so that makes this a little easier problem. I think if you remember the ones we did in the first part of the semester, sometimes we changed it up and said, things were going out of A, faster than they were coming in. So the level would sink or the level would rise if you had it the other way around. Okay, so but what we're going to do is basically the same thing we did with those other problems in the first part of the semester. We're going to look at the rate of change of X1 and think about it as the rate in of the salt minus the rate out. The rate in minus the rate out. So let's look at the in rates for that. The in rates in tank A are 3 gallons per minute. Now this is salt we're talking about, the rate of change of the salt. So we have to consider the concentration here. So that's 3 gallons per minute times, this is pure water right here. So the salt in it is 0 pounds per gallon. Okay, that's why that zero's there, because the water coming in at that point is pure water. If you look at these units, this is what I sort of counseled you to do when we were looking at these problems before, and this helps you sort of set your equation up. If you look at these units, gallons cancel out and you get pounds per minute. Well, that's salt you're talking about, the pounds per minute of salt. That's how you want it to line up. All right, so the rate out, so we'll subtract, oh, sorry, I've got one more rate in. There's more stuff coming into A from tank B. So it's coming in at 1 gallon per minute. So I'm looking at this piece right here now, 1 gallon per minute. And we don't really know how much salt is in B at any time. So we'll just say X2, that's what we let X2 be the amount of salt in it at any time. And the concentration will be X2 pounds per the 50 gallons that are in there. And I know there are 50 gallons in there because both of these tanks start out with 50 gallons. And we said that things weren't shifting that way because we had the same rates in as out in the whole system, okay? So that thing right there, this whole thing right here is your rate in, okay? The rate out, if you're looking at out of A, the only pipe that's going out of A is this one right here. And it's going 4 gallons per minute. Because we're getting salt, we've got salt in here, all right, and there's more salt coming into it, we really don't know how much salt is in it, but it's just X1 pounds of salt per the 50 gallons of water that are in it, okay? So we look at the concentration there. And again, the gallons cancel and you'll get pounds per minute right there. So there's an equation that describes the rates in and out of tank A. Okay, let's look at tank B. Let's see if I can get it down here. It's gonna get cut off. All right, so I'll scroll back and forth, guys. All right, tank B, again, it's rate in. So it's rate salt in minus rate out. So I'm going to go back and look at rate in on tank B. What's coming into tank B is the stuff that's coming in down here. Everything else is going out. So the stuff that's coming in down here is going to be 4 gallons per minute. So that's what I get right there, 4 gallons per minute. I don't know how much salt there is in A at this point because it's changing. So I'll put X1 over the 50 gallons that I know are going to be in there all the time. So that's the rate in. Again, gallons per minute, pounds per gallon, gallons cancel out. I've got pounds per minute. The X1, the amount of fluid, I'll say the amount of mixture in the tanks is not changing. It's staying at 50. The amount of salt is. So I have to figure out that ratio there. Okay, the second part says minus the rate out. Okay, the rate out of B. Let's look at the rate out of B. Now, what's coming out of B? There are actually 2 things coming out of B. That one right there, and that one right there. All right, all of that stuff's getting pumped out of B. So what happens in this piece is we're going to subtract off those rates out. So we'll look at it. That top one was 1 gallon per minute. I did it second, but that's all right. 1 gallon per minute, and X2 is the amount in B divided by the amount of the steady amount of the mixture right there. The other one was coming out this way. And that was 3 gallons per minute and X2 over 50. So that's why I got this thing right here. All right, 3 gallons per minute, X2 over 50. So that's the rate out. Now, it's, let's write down what we've got here. We know what the units are gonna be. So let's write down what the differential equations are here. Notice I've got two things working at the same time. I'm gonna have two differential equations here. So when I simplify these things, let's just see, I wind up with, well, let's see if I can get it high enough here. There we go, I think, yeah. So this one right here was dx1 dt. Here's the simplified form of those things right there. All right, we wind up with, just simplifying this thing. That thing right there is 0. We get 1 over 50 here, x2. So that's where this piece right here comes in from right there. And then in this one, we get minus 4 x1 over 50, and that's where I reduce that to 2/25, and that's where that one comes from. So there's an equation. It's a differential equation with two things that are changing in it. If I look at x2, this 4 over 50 again here gives me the 2/25 right there. Right there. And then if you look at this back piece, it's minus 3 over 50 minus 1 over 50, which is minus 4 over 50, which gives me that minus 2 2/25 x2 right there. Okay. So the conditions they're going to give me are that in the first tank at the beginning of the process, there was 25 pounds of salt. In the second tank, they're going to say there was none. Okay, so we start out with none, but it gets salt in it as the process takes hold. This thing right here, guys, is called a system of differential equations. Okay, it's called a system of differential equations. And in general, I'm not going to solve that one right now. We'll come back to it. But in general, here's what that looks like. It says a system of linear equations consists of two or more equations that contain derivatives of two or more unknown functions. So for us, it was x1 and x2. We didn't know how much salt in either tank. Of a single independent variable t. Our independent variable t was time. What's happening to the salt in the tank with respect to time. And so our solution, we want our solution to look like how much salt is in tank 1, or A, at time 1, or at any time t. Same thing about tank B. All right, let me give you a couple of examples, and then we'll call it quits for the day. Okay. And remind you of some notation that we're going to use. If you looked at this one right here, you've got a second derivative, first derivatives in this one. These are all functions of t. You've got the x and the y also on this side, the functions. And here's your independent variables of t. The problem that we just had these were zeros. This is non-homogeneous here. One thing we're going to do with these is move everything over, move all the x's and y's over. So x double prime plus 2x prime minus x plus y double prime minus 3y is going to be sine t. So it's kind of easy for you to see there. The function on the right is your function of t, and on your left are all your functions of which you're going to take the derivatives. If you did this other one like this, you'd have x prime. Oops, x prime. Sorry. That's x prime. I'm going to bring this 4x over, plus 4x, plus y prime from right there, that one right there, and then bring the 2y over. So minus 2y, and that would be e to the minus 2. So what we have there, again, is a system of linear equations consisting of two or more equations, x and y in this case, that contain derivatives, okay, of two or more unknown functions, which are x and y. Both of them are a function of time. So on this right-hand side, we have these other functions that have to do with time. Another example, if I looked at this one, this is 3 equations and 3 variables here. We got 3 things changing here, guys. This was as if we had 3 tanks. Okay, we put all the X, Y, Z's and so forth on the left-hand side, and on the right, there's nothing but functions of t. Okay. Now, what I want to show you, what I want to remind you of, and I'm not going to solve this today, but what I want to remind you of is the way I want to tell you how I'm going to write it, and then we'll be set up to do what we need to do on Monday. We're going to use the operator notation. We mentioned that briefly back in section 4.3 or something like that. But the operator notation turns out to be the easiest way to solve these things. So for example, if I took this one that I did, I think it's this one right here, and I said, I'm going to write this in operator notation. Well, operator notation did this. It's called D the operator, and D is take the derivative of something. And what you did in these X terms, you took a second derivative of X, 2 times the first derivative minus the function itself. It almost looks like you're factoring here, guys, but you're saying we're going to operate on the function X by taking its second derivative. So in other words, D2 is equivalent to that. 2D is 2 times the first derivative, because that's D to the first there. So 2x prime minus 1 is just x. So if you multiply this out, it would look like d2x, which just means x double prime, plus 2dx, which just means 2x prime, minus 1, which just means minus x. Okay. If you look at this other one here, y double prime is d2. We don't have a y prime in there, so we're not going to have a d to the first. We're going to have a y. So in operator notation, that thing looks like that. And we're operating on the function y. Second derivative of y minus third derivative, minus 3 times the function itself. That's all that is. So operator notation. All right, I am not going to go through a solution today because I just don't want to get started on this. I want to get start fresh on Monday. But what I want you to do is, and I'm even going to change this. I'm going to say in one, and this will help you to have done some of your homework starting Monday night. I just want you to take number 1, number 3, and number 5, and put them in operator notation. Put in operator notation. I think that in all the books, but just to make sure, I'm gonna put this section online like I put the other sections online for those of you who have a different edition. I think 1, 3, and 5 are the same in 10 and 11. I'd be really surprised if they changed it. I'd be less surprised if the whole darn section was somewhere else in the book. I mean, they keep changing them back and forth between chapters. But I will make sure that these problems on that page get put online. That will not take you long. All you have to do is just move all the X's and Y's over, write that operator notation, and we're going to need it like that in order to use the method I'm going to solve this with. Okay. Anybody have any questions? Anybody have any questions? Okay. Again, if you can get your homework to me sometime before tomorrow morning, that'll be great. You know, if you didn't have a chance to figure out that first problem because it had that hyperbolic sign on it. Hyperbolic signs are really big in applied mathematics. I don't have a lot of time to do it anymore in Calc 2, and that makes me sad. But because my degree's in applied mathematics, that's what I always want to do. I want to do what my Calc 2 student that I've got right now keeps asking me. I can't go 5 sentences without her saying, well, what am I going to do with this? No, what am I going to do with this? I was like, and I want to tell her, but she doesn't have enough chops for me to tell her yet. Okay. So, so I hope you have a good weekend, and we'll come back Monday, and we've got basically 2 full weeks left, and that's it. So we'll be doing these systems of equations, and we'll be doing some, I think we're going to do spring problems versus some of the theory problems, because I really, like I said, I want to do applications in the end of this so you can see how it's used. All right, if there are no questions, I will see you guys on Monday, and hopefully by that time I'll have all your homework back. And then there's the Cauchy-Euler homework that's due. If you have extra time this weekend, go ahead and try some of the Cauchy-Euler stuff. So if you have questions on it, you can ask me on Monday. All right, see you Monday. Have a nice weekend. Bye.